2 says that what? It says that wherever you give your initial data, okay, that coefficient can't vanish. But in our case, the leading coefficient is x squared, and that vanishes at x equal to 0. Okay? And that's why that theorem is not applicable. Okay? If I were to give this problem and give, for example, y of 1 and y prime of 1, there'd be no problem, right? Because that both conditions are satisfied. Okay. This is what's called a singular differential equation, and these do occur in practice. Specifically, this is what's called a Euler equation. It comes up in elasticity theory, like in buckling and things like that. And there's a physical explanation as to why the solution is not unique. Okay? So, okay. Now I want to talk just briefly about boundary value problems. I'll make them second order just for simplicity. Okay? We're not going to really deal much with boundary value problems, but just so that you know the difference, okay? The distinguishing feature between initial value problems and boundary value problems is that when you have an initial value problem, all the data is prescribed at the same point. There are certain problems where that just doesn't make sense. So let me give you an example, okay? This is if when you take courses, and I haven't taken this yet, in beams, okay? Plates and beams. This is supposed to be the neutral axis of the beam. Let's say it's a thin beam, okay? There's an equation that describes the deflection, the static deflection of that under applied loading. And it's basically the following. It's EI times the fourth derivative of y with respect to x is equal to W of x, where W of x is the loading, the unit length. Okay? So W would be pounds per foot or something like that. It's a distributed loading on beams of external forces. Maybe it's like in your car when you have an antenna and then there's a wind load that goes, right? It bends when that happens. Okay? Or it could be a building even. The buildings aren't modeled by other Bernoulli beams, so a car antenna is probably a better example. Okay? So this is the equation for, it's called Euler's equation for the bending of a beam. It's actually an approximation. It's linearized. It becomes much more complicated with the nonlinear model. Let me just tell you a little bit about what the coefficients are. Okay, y would be the deflection of the beam from the initial position. So the beam is straight over here, unstrained. Okay, just going between say x equal to 0, and maybe this is x equal to L, where L is the length of the beam when it's unstretched. Okay, and then someone puts a loading on it. It's obviously going to deform. And this is the static case, so it's in static equilibrium, but obviously it's deformed because there's loading on it, okay? So W of x, you know what that is, that's loading unit length. X is the beam length, x is the coordinate along the x-axis between 0 and L, and y is the deflection of the beam. This is all small deflection theory, okay? What's this EI? Okay, it's just called the bending stiffness, and it makes perfect physical sense why I wrote as two parameters over here. Okay, hopefully you've taken a little of mechanics and materials. E is the Young's modulus, okay? You go to a lab, basically you take a rod and you put a certain load on it. The modulus is like the spring constant, basically, but for a rod, okay? It tells you the stress versus the strain. Basically, the Young's modulus is the first part of that curve. So that depends upon the material, right? Is it copper? Is it wood? Is it lead, right? So Young's modulus is a property of the material. Okay, why is there another parameter in there? That I is basically, people refer to as the moment of inertia. It's really a bad terminology. It's called the area moment of inertia. Okay, it has units of feet to the fourth. Let me just suffice to say, I don't go into a whole big discussion over here, it's a property of the cross section. Now, think about it. That certainly has to be into the equation, right? Suppose I had two beams of identical material. So the Young copper, Young's modulus, okay? So, and one cross section is like rectangular, okay? This is looking, head on to the beam, and the other one has a circular cross section, okay? I think you could easily, kind of surmise that given the same loading, these beams will bend different amounts, right? Because the kind of what's called the stiffness is a function not only of the material but also how the cross section is constructed, and that's why you have this EI in it. It's this product over here, which is a reflection of those two properties. Okay, so. You have this equation now, okay? And what happens is depends upon the supports, okay? You can support a beam in different ways. The way I drew it over here is basically you can't leave it at 0. Imagine there's a wall over here, okay? And it's just stuck into the wall, okay? That's called the geometric boundary condition. What would be the conditions on y at x equal to 0? y of 0 is equal to 0, right? It's stuck in the wall over here. It's not going to move. And also, it has a 0 slope. So we'd say that dy dx at 0 is equal to 0. Okay? This end, basically, at the right, is the way I drew it, it's free. Okay? There's nothing stopping it. And you'll learn that when you take mechanics of materials, that the condition when a beam is free is has no moment, no shear. Okay? Because the bending moment something would have to be twisting it, and the shear would have to be something that would be pushing up on it over there. So, at x equal to L, the bending moment is 0 and the shear force is 0. And when you study the Euler-Bernoulli beam, you'll find out that the bending moment is proportional to the second derivative. So that equals 0, and the shear is proportional to the third derivative. Okay? So what happens here is that we have a fourth order equation. Okay? We have 4 conditions, but because of the physics of the problem, just naturally they're going to be specified at 2 different points. 2 at the root of the beam and 2 at the free end of the beam. Okay? Sometimes it would be different if it was like, suppose the beam was like this, where, okay, deflected, let's say, and there's like a pin connection at both ends. Okay? Then it would be something like this. Okay? At a pinned end, what would happen is that pinned. Okay, this is called clamp free. Okay, if it's pinned, then at a pinned end, the condition physically is that you have a 0 displacement, right? And also a 0 bending moment. It's like a pure, there's no friction there. And the boundary conditions would be then at 0 and L, y vanishes and dy dx vanishes, 2 at both ends, okay? And if you look at books in vibration and stuff like this, okay, they have just pages and pages of solutions of these types of problems with different types of boundary conditions, okay? And they get pretty involved, okay, but you actually can do it analytically. Okay, so here's a little thing on where we get boundary value problems, okay? And for a second order equation, I think this is kind of, you can see it right away. See, going back to the beam problem again, depending upon how the physical constraints are, you may specify the value of y, or maybe some of its derivatives. Sometimes even a linear combination of y's derivatives. If there was a spring over here, okay, then the boundary condition at L would involve a linear combination of y and its first derivative. Okay? So these are called boundary value problems now. And I'll go down to lower order like the book does. Okay? And again, you could take a whole course in boundary value problems. Okay? And the thing which I guess I want to show you is that the same type of equations, even very simple ones, when you change it from an initial value problem to a boundary value problem, the existence uniqueness theorem is much more involved. We're not going to go into it, but I'll just show you how it kind of just breaks down, okay, by an example. So we may have something like this. Let's go to second order. A2 of x, y double prime, plus A1 of x, y prime, right, plus A0 of x times y equals some function of x. That's really that guy over there with n equal to 2, right? And I can have different types of boundary conditions. For example, y at x equal to a can be specified as a certain number, and y at x equal to b can be specified as a certain number. That's what happened over here, right? We specified y at 0 at 0 is something, y at L is something. You also can have things like this. You may have y of a being prescribed, okay, and the derivative at b being prescribed. Let's just call that b tilde or something like that, okay? Or even a linear combination of them, okay? The important thing over here is that this is a second order boundary value problem. So basically, again, there are 2 endpoints, and you have to specify in total 2 conditions, okay? In the first one, I specified the value of y at a and y at b. Maybe it's the value of y of a and the derivative of b. Or maybe the derivative of a and the derivative of b. Okay, all those possibilities exist, depending upon the physics of the problem. Okay. Now what we're going to show is that even if we keep all these, I'll leave this one up for the initial value problem, even if I satisfy all these 2 conditions for a boundary value problem, solution, anything can happen. No solution can happen, a unique and a non-unique. And the best way to do it is an example. The book has an example, which I'm just going to present, okay? Again, we haven't yet solved any of these equations, but I just want to get your feet wet on getting familiar with these. Okay, so here's the equation I'm going to look at. The second derivative of x with respect to time, okay, plus 16x is equal to 0. It's a simple oscillator, okay? Okay, the general solution, again, you'll have to take my word on it, but by the end of next week, you won't have to. The general solution is x of t equals some arbitrary constant cosine of 4t plus another arbitrary constant times the sine of 4t. Okay? Two arbitrary constants, that's what we expect because it's a second order equation. And the best you can do at this point is just plug it in, right? Just do x dot, x double dot, add 16x, and you can verify that it's equal to 0 identically. Okay. And again, you have to be comfortable now the dependent variable is x and the independent variable is time, t. In other words, y and x. Okay. Let's now look at three different problems, three different kinds of boundary value problems. The first one, it says solve this equation where x of 0 is equal to 0, okay, and x at pi over 2 is equal to 0, okay? Now remember, what I wrote down here is an existence uniqueness theorem specifically for an initial value problem. Don't make the mistake thinking this also happens to work for the boundary value problem, okay? And we'll see that it doesn't, okay? What do we have over here?
So these are the endpoints?
Endpoints, yeah. 0 and pi over 2. Yeah. Like in being it was 0L, now it's just 0 and pi over 2. Okay, let's just solve it and see what happens over here. Okay, you can do that. We did this like the second week. Remember, in some of the homework, they gave you the solution. They say find C1 and C2. Okay. So let's apply the initial condition x of 0 equals 0, okay? And get the constants. Well, x of 0 is just C sub 1, right? Sine of 0 is 0. So C1 is equal to 0, okay? So now that means x of t is C2 arbitrary constant sine of 4t. Now let's apply the second boundary condition, and maybe we can get C2. What's x evaluated at t equals pi over 2? You get c sub 2 sine, what's 4 pi over 2? 2 pi. That's 0. Because it's sine 2 pi, no matter what C2 is. So C2 is indeterminate. Okay? So what happened over here is that even though we had a second order equation and we had two pieces of data, it's a boundary value problem. We specified not the value x at 0 and dx dt at 0, but x at 0 and x at another endpoint, pi over 2. And what we verified is that the general solution is C2 sine 4t, where c is an arbitrary constant. Now, all the conditions of that term are applicable over here, right? What's the coefficient? 1 is continuous. The coefficient of dx dt is 0. The coefficient of x is 16. The right-hand side is continuous. See? So all conditions 1 and 2 are satisfied, but the solution is not unique. Not a contradiction, because this talked about the initial value problem. This is a boundary value problem. Okay, it's different. Okay? So right away, you can see that even a simple equation like this, obviously the theory of boundary value problems is quite more intricate than initial value problems. Okay? And we're not going to really get into that in this course. But you should, boundary value problems, of course, occur all the time. When you take other engineering courses, structures, vibration, heat transfer, fluid mechanics, many times you'll get boundary value problems. Okay? And just be aware that it's not so clear that the solution always exists and that it's unique. Hopefully, though, if you're doing a physical problem and you have, the right data, most of the time people don't worry about it because they say, but I can tell you some interesting stories, especially in the history of boundary layers, where people had very complicated equations, boundary value problems, and then they would solve them numerically, and then they would get different results, and then a more careful analysis revealed that the solution wasn't unique. It was some type of slip condition that wasn't accompanied. Okay, so it's something. These terms are not just esoteric and of mathematical use. Many times they can be used to just check the fact that you want to make sure the solution is unique. When you go to the computer, it's not going to tell you if it's, it'll get one solution depending upon the numerical method it uses, okay? So it's very important to know that before you even go to the computer. Okay, so here we have a second order equation, two boundary conditions, non-unique solution, infinite number of solutions. Okay, let me go to problem number 2 that's related to this. Problem B. We'll keep x of 0 is equal to 0, okay, keep that one. Let's change the boundary condition at the right end to be x evaluated at pi over 8 is equal to 0. Okay, let's see what happens there. Okay, the general solution is still c1 cos 4t plus c2 sine 4t. X of 0 is still 0, so c1 is equal to 0, right? So I'm still at the point now where x of t, before the other condition is applied, is c2 sine of 4t. Okay. Now let's apply the boundary condition at pi over 8. Okay, what's my solution, therefore, at t equals pi over 8? It's c sub 2 sine of 4 pi over 8, which is the sine of pi over 2. And everybody knows that the sine of 90 degrees is 1, that's c2, but x of pi over 8 has to be 0. So in this case, you have c1 equal to 0 and c2 equals 0, so here the only solution is the trivial solution. Okay? Interesting, okay? Now just changing that one boundary condition from x of pi over 2 equal to 0 to x of pi over 8 equal to 0, we went from infinite number of solutions to a trivial solution. Okay, what's next? Let me see if I can come up with some data that gives you no solution. That'll be part C. Okay. Part C. Same differential equation. I'll keep x of 0 equal to 0. Okay. And what do we have here? X of pi over 2 should be 1. That seems I should be able to do that, right? Okay. So, x of t. Again, it's the same differential equation we're dealing with in all these three cases. So the general solution is c1 cos 4t, c2 sine 4t. And we set x of 0 equal to 0, we find, just like before, c1 is equal to 0. So x of t is equal to c sub 2 times the sine of 4t, same as before. Okay. Let's evaluate x at pi over 2.